Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff, the AAS Journal Author Series. And I am very happy to have Brian Metzger and Rodrigo Fernández with us today. Hey, Brian. Hey, Rodrigo.
Hello.
Hey, Brian.
How you guys doing today?
Pretty good so far.
It is September 9th, 2021. So we're heading into the deeper part of summer here in Phoenix, or because we won't get fall till mid-October or so. So let's go with New York first. I heard there's been lots of rain there recently.
Yeah, Ida brought in, I think we got more rain in 1 hour at Central Park than had ever occurred in recorded history. So it's
Wow.
been raining a lot here. We got a bit more today, but not as bad. I think we were sideswiped. I forget the name of the hurricane, but anyways, we're doing okay. Today is also the first day of classes at Columbia. So
are you going in person, or is it all virtual, or what's
we are in person, basically 100%. So it's quite a contrast on campus here.
I bet. And Rodrigo, where are you at?
Yeah, I'm in Edmonton, Alberta, Canada. So I'm at the University of Alberta. And yeah, fall is already starting here. The trees are getting yellow. So for reference, Edmonton, I believe, is one of the northernmost city with more than 1 million people in North America. It's pretty far north. And so it's getting cold pretty fast. And we go from plus 25 to minus 40, right? In like a span of months, right? So yeah, so we also are in person teaching. So we started last week.
Okay.
Everybody masked. There's not required to be vaccinated. It's like a recommendation. Yeah. But yeah, I wear an N95 mask while I teach, and so that's the state of things.
Cool. Let's see. I started teaching about 2 weeks ago, 3 weeks ago, something like that. So we start pretty early, and we also end pretty early. And ASU is back in person, although all of my teaching is online, so doesn't really matter in that sense. But yeah, we're back. So. And hopefully at some point in 2022, we'll all be normal and I'll get to interview you guys in person. That would be great. Very good. Rodrigo, what do you like to do for research?
Yeah, so I am a theorist, and in particular, like computational, the computational part of theory, focus primarily on things that explode in the stellar context. So I call it astrophysical transients and compact objects. So that really mean neutron stars and black holes and the explosions associated with them.
Very cool.
I like to ask questions that can be answered with computational simulations. And of course, the goal is to make predictions that then observers can compare with what they find, and we learn.
Indeed.
With the universe.
Brian, how about you? What do you like to do for research?
Work on a lot of topics. One umbrella connecting them is probably time domain phenomena. So things that explode as well, supernova, neutron star mergers, stellar mergers. And, I like to make use of both, analytic pen and paper stuff, and then, more detailed calculations. And I like to work with, the expert numericists, people like Rodrigo. So
there's a shout out. Very cool. And that is going to bring us to this very lovely APJ letter. From neutrino to photon-cooled in 3 years. Can fallback accretion explain the X-ray excess in GW 170817? And Rodrigo and Brian, take us away.
Okay, great. So I think everyone's probably heard about GW 17817. It was the neutron star merger that LIGO detected its first one back in 2017. And it produced electromagnetic emission, across the whole spectrum. Within a few days, there was this optical infrared kilonova, which was powered by the radioactive decay of matter that was ejected during the neutron star merger. There was a X-ray and radio and gamma ray jet. We actually saw prompt gamma rays from the jet, and we also saw X-ray and radio that were produced as the jet, which we think, I'll talk about the origin in a second, we think it was powered by accretion onto a newly formed black hole. But as that jet interacted with the ISM surrounding the merger, it gave rise to this multi-wavelength afterglow that I assume everyone's heard quite a bit about. And so the basic picture, is that the two neutron stars merge. They eject some matter during that process, but they form a black hole surrounded by an accretion disk, and it's the accretion of that disk onto the black hole that we think powers the gamma ray burst. And also the accretion disk onto the black hole produces winds of material, neutron-rich material that comes off of these winds is an important source for the kilonova, for the radioactive material.
Cool.
After the X-rays from this event peaked at about 100 days after the merger, they began to decay. And we understand this because we're, outside the line of sight of the jet, and it's, beginning to slow down as it runs into the ISM. And so the X-rays, for the last 3 years after the merger, the X-rays were sort of, monotonically decreasing.
Mm-hmm.
And then recently, the last, year or so, Chandra did some really deep X-ray observations of 17817. And what it found was a bit of an excess. It found more X-ray photons than it would have expected just following the expected decay of the afterglow.
Okay.
And so there's, some hints that there's an extra, the claim significance is around 5 sigma for an excess above the best fit afterglow model. Okay. And another thing is they don't see radio emission that's also, it's not a bright rebrightening, but they don't see a radio excess. And so it suggests there's something that's producing extra X-rays. And so one of the models that we're exploring in this paper for the X-rays is whether we are seeing X-rays coming from the newly formed black hole, which prior to this 3 years was kind of enshrouded in all of the ejecta from the merger. And about 3 years after, that ejecta is now becoming transparent to X-rays, and we can potentially see the black hole in the center. And it works out, nice as a model. The black hole, if it's accreting, near the Eddington rate, should be producing, X-rays. Mm-hmm. It's about the time we might expect those X-rays to turn on. And there are other explanations, I should say, for the X-ray excess. It may be a different component of the ejecta interacting with the ISM, but the issue, or one of the open questions, is can we explain it by accretion onto the newly formed black hole? And the question there is, do we have enough accretion at such late times, 3 years after the merger? Is there enough matter that's continually being fed into the black hole that we can explain the luminosity of the excess? Okay. And so the goal of this paper was to study the very late time, or at least as late as we can, evolution of these systems to determine, if we can, estimate what is that accretion rate. And so there are kind of 2 forms of ejecta in the merger. There's the matter that is ejected when the neutron stars collide, or right after that. We call that the dynamical ejecta. Mm-hmm. There's not a whole lot of that material, and it has a high velocity, so it doesn't make a great source of matter that's going to be falling back at late times in great quantities. Yeah. But the second source of ejecta, which we actually think was the most important in 17817, and Rodrigo and I have done quite a bit of work on this, are outflows from the accretion disk, as I said, the one that's powering the GRB jet. And so what we really wanted to study in this paper was to take a simulation of the post-merger accretion disk, follow it as late as we can, and Rodrigo will say it turns out as late as we can follow it is about 30 seconds, after the merger, which doesn't sound like a lot, but it's billion or millions of dynamical times at the black hole. Uh-huh. And so we want to try to figure out what is the physics that's controlling the rate the black hole is getting matter from the accretion disk at late times, and can we explain this X-ray excess? So maybe with that, we have some questions. Maybe I could hand off, and Rodrigo could describe our simulations, and then I could come back and discuss some of the results. So maybe zooming in on actually figure 2, or maybe that would be the best one, Rodrigo. No.
Where would you like to start?
Sure. Maybe the table.
Okay.
Just to begin with, just to explain like exactly parameters and so on. Yeah. So as Brian said, we're interested in understanding whether accretion can supply this late time emission. And so from what we already know from all the studies that have been done by others and us on the disk evolution, essentially after some time the disk should enter some kind of steady state, like even self-similar, one would say, because there's just one energy source, right? So basically these are accretion disks that form after the merger. So it's material that is not gravitationally unbound, but it's just bound, but has sufficient angular momentum to form a disk around presumably a hypermassive neutron star that collapsed to a black hole over tens of milliseconds. But for simplicity here, we're assuming that we start with a black hole from the beginning, and that doesn't really make a difference at late times. early times, if we're talking about kilonova and electron fraction and blue versus red, that can affect that, but at late times, we think it doesn't. So we start with a black hole accretion disk, and so then we choose parameters that are as consistent as possible with what was inferred from 170817. So a black hole mass of 2.65 solar masses, a disk mass of 0.1 solar mass, and that is not. I mean, there's a range that can go up to 0.2 or down to 0.05, depending on the equation of state, which determines how much mass is left as a disk.
Okay.
These are hydrodynamic simulations, right? They're not MHD. We think that the MRI, the magnetic rotational instability, transport angular momentum in real astrophysical disks, but to model that reliably, you need to do a 3D simulation. Right?
Okay. Yeah.
So that's already at the limit of what can be done out to, I don't know, 10 seconds at the most. Right? And so these are hydro simulations, and why can we do that and still have a reasonable conclusion? Is that this kind of a advertising my own work to some extent, but not only mine. Brian and also Daniel Siegel have done these studies, and other groups now. Basically, a few 3D MHD simulations of accretion disk in this context have been made. So with the neutrinos, with microphysics as reasonably as possible, and what's been found is that at early times the magnetic field, let's say Lorentz force, dominates the dynamics, because that's what happens, right? But once the MRI turns on and the turbulence starts to be dissipated and the neutrino emission shuts down, which has to happen because the density goes down, then there's not a lot of difference between how alpha viscosity looks like in terms of heating rates and mass ejection versus MRI turbulent dissipation. Right? Okay. So we compare the late time, so we're talking about after a few seconds, accretion rate and outflow rate, and they look pretty similar. I mean, the slopes change a little bit, but overall you can say it's not a bad approximation to use an alpha viscosity hydro simulation for late time studies of the accretion disk. Right? And so these are hydro simulations in 2D with alpha viscosity. And I don't know if there are questions.
No, you're doing great.
No? Yeah, okay. So then we have the time, right? And so Brian touched on this. So for reference, the orbital time at the accretion disk initial radius, which is about 50 kilometers, given though that black hole mass is about 3 milliseconds.
Yeah.
Right? So here we're talking 10,000 orbits at the initial disk position. So Brian talked about the dynamical time. Like that's basically the light crossing time at the black hole horizon. That's 1 million of those. Right? If you were to do an GRMHD simulation, that's really the number of dynamical times you would be modeling. So it's a long simulation.
Indeed.
It took 2 to 3 months, I would say, of running time on 64 cores. Okay. In Canadian clusters, the Beluga cluster. Thank you to Calcul Quebec for that time.
There's a shout out.
Yeah, it's good. And so the way it goes is that one starts with an equilibrium torus, right? Okay. But this is a whole separate set of questions. So what are your initial conditions? We could map from a merger simulation, but that's already introducing some complications. Do you have to axis symmetrize a 3D hydro? We have done it before in one instance, at least us, other groups probably have done it too. But here we try to start with relatively clean initial conditions, and then of course the disk starts accreting. Neutrino cooling is important initially, so it's relatively imbalanced cooling and heating from viscosity into the disk, so it's not too puffy initially. Okay. But eventually the neutrinos shut down and the disk becomes relatively inefficient, right? Because viscosity is just injecting heat, so it's puffy, and essentially part of the disk starts becoming thermally unbound, right? So some people call this disk evaporation. I don't quite like the term, but it's you're thermally ejecting.
It's descriptive.
Right? Exactly, right? And so then part of the disk is accreted, part of the disk is ejected, right? For these parameters, usually we get 20% unbound, and 80% accreted into the black hole, right? As measured at 10 seconds, right, or 12 seconds, which is when most of the mass either goes out and goes in, right? Now for this study, we are going later than that. So the accretion rates at later times do not really change how much mass was accreted or ejected, because it's a tiny amounts. We want to know how it keeps going, right? And in particular, after the neutrinos have shut down and after the temperature is below something like 5 times 10 to the 9, there's no more nuclear dissociation, right? Like nucleons into alpha particles, or vice versa, alpha particles into nucleons. That's an energy source, energy sink, sorry.
Yes.
Once that goes away, the only energy injection in the problem is alpha viscosity, right? So we expect a power law decay.
So maybe just to augment that, that's why we had to run the simulation so long, because initially this disk is free nucleons, but as it cools, they recombine. And so we have to follow it long enough for it to cool to follow that energy injection and make sure that we're kind of past that point in the evolution.
Yep. Let's see. And so
just let me finish the thought before we transition. So then we enter into a power law regime. And then maybe you can go to figure 1. I think that's
very nice.
So after a while, you see that the accretion rate in the alpha 0.03 model, which is the black line, the noisy black line, basically becomes roughly a power law after 10 seconds.
Okay. Yes.
Yeah, that's the accretion rate into the black hole.
Yep.
And so after that, we say, okay, there's nothing else happening here, so it should just keep going. That's the hypothesis.
We could talk a bit more. I think maybe the figure 2 also would help to show as well, which shows one of the late snapshots.
From the simulation? I think that's figure 2.
Yeah, it may be a little.
Yeah, let's go ahead and just walk through the simulations here and come back to figure 1.
Do you want to?
Sorry, I mean,
No. I'm not. I'm just saying so that kind of what you have in mind. I think it's good, and then I can just maybe supplement that.
Yeah. So I mean, this is showing the final snapshot. And basically, this is the energy of the matter, essentially total energy, kinetic, thermal, gravitational. So things that are blue are bound to the black hole, things that are red are unbound. And what you're seeing is this is all at the same time snapshot, but we're zooming in on different scales. So the leftmost scale is closest to the black hole, which is
here's the box. Okay.
And then we zoom out progressively to the right.
Got it. Okay. Are you with you?
So on the left, we have scales of kind of 100 kilometers, and then on the right, we have scales of like solar radius kind of thing.
Right.
So what you see on the rightmost scale, say, is that after 35 seconds, you've created this kind of big bound cloud of debris. Basically, the early phases when you're ejecting a lot of mass, they do eject a lot of mass in this red material, but they also create this bound cloud of material that's continuing to rain back in on the black hole.
Yes.
At late times, and when it lands back, so that material is not in a disk. The disk is centrifugally supported close to the black hole, but as matter returns to the black hole, it gets heated viscously, and then it gets driven in these outflows, which tend to come out more at the higher latitudes. So you can see these kind of red plumes,
right,
that come out, say on the left panel at the top and bottom. So
yeah.
So we have this picture where the early phase of the merger does eject a bunch of mass, but it also creates a bound cloud, which then continues to rain back in on the accretion flow. And while the disk can't cool, that matter will mostly be ejected in winds. So it doesn't really make it into the black hole because it's landing in the disk, getting heated by viscosity, but then it has no, at these late times, the disk temperature is so low that neutrinos can't really cool you anymore.
Got it.
And so that's kind of what Rodrigo what I think was getting at with this curve. And the reason that the black hole accretion rate was falling so sharply on this plot above is because the black hole is becoming very much a fussy eater. It's that black line is dropping like a rock.
Yeah.
And if you notice in figure 1, like there's this horizontal dot dash line at the top that basically indicates that above that accretion rate, neutrino cooling is efficient. And you can see that there's not a lot of fluctuation because the disk is pretty much laminar, right?
Right.
And the red curve, which is something connected to what Brian was talking about, is essentially the rate of change of the bound mass.
Okay.
In the domain, right? And so both curves track one another when neutrino cooling is efficient. Right? Okay. So once neutrino cooling is not efficient anymore, they decouple.
So yeah,
they lost less accretion onto the black hole.
Here, once you're up there, once you hit the limit, they separate.
Exactly. So the black line is like the rate at which the black hole is eating matter, and the red line is kind of the rate at which matter from this cloud is falling back. So at early times, they match each other. The black hole is accreting most of the matter, but then they begin to diverge. So matter that's coming back is being unbound in these winds rather than being accreted.
Cool.
And I guess the key point, to jump to the punchline, is that there are two ways these disks can cool. One is at very high accretion rates. When they're hot enough, they can cool through neutrinos. But the other way they can cool is at very, very low, in this regard, low accretion rates. Because these, so I guess I could just describe this figure, but basically at very low accretion rates, the disk can cool through photons once they drop below the photon Eddington rate.
Yep, right there.
Exactly. And so even though at the end of our simulation, 35 seconds, the black hole is a fussy eater, once we get out to 3 years, now the fallback rate of this cloud of debris is dropping low enough that the black hole should start to be able to accrete that matter again because it can cool through photons.
Very nice.
And so the left figure, so just to summarize, so the left axis is the fallback rate or accretion rate, and the right axis is showing you the accretion luminosity, the 0.1 m dot c squared. So that would be kind of the, if you could convert this accretion power into a X-ray flux, that's what it would be roughly. And the point is, although our black lines undershoot, so the data from Chandra is that square on the right that says X-ray. That one exactly. So if you were just to follow our black line, you would undershoot that enormously. The dotted black line. But when you account for if you follow the fallback rate, the rate that will become the accretion rate once it's able to cool, then we find that these simulations may be able to go through the X-ray axis. So it does seem, at least for our alpha 0.03 simulation, that within our uncertainty the ability for us to extrapolate the simulation results, we are able to reach that X-ray axis. So that's why the paper is called From Neutrino to Photon-cooled in 3 years, because it's this a falling accretion rate. But as you can see, it's not a home run. I mean, if the higher alpha model, it undershoots. And so I think
you're early, right? It comes off too early, right?
Yeah. And so I think the conclusion of this paper is this is plausible, but I wouldn't say we've shown that this, definitely is the origin of the X-ray axis. It's just that we have enough matter from this cloud that's falling back that if it is able to continue at that rate and eventually photon cool, then we could get the X-ray axis.
Nice, very good, very good.
Part of the reason this alpha 0.1 simulation is relevant is that when we did that study I mentioned before comparing GRMHD with hydro, GRMHD falls in between 0.03 and 0.1. Right?
Okay.
And so 0.03 is our best case, right? But GRMHD suggests that it might not be the most realistic. So as Brian said, this is a plausibility argument, subject to a whole bunch of caveats, I would say.
The other thing we put on this plot, just so everybody, we put the kilonova on here. So this is the thermal emission, which was detected at early times by a whole slew of telescopes for the first weeks. And then there was actually a couple detections / upper limits from Spitzer.
These.
A couple months after the event. And so one of the concerns with the fallback model was, okay, well, you're producing all of these X-rays, they should be absorbed by the ejecta and reprocessed into optical UV radiation. So the trick of this model is it has to undershoot the kilonova and then go back up to reach the X-ray excess. So it's a bit of a balancing act.
Right. Right.
You have to say,
Totally,
when the kilonova was going on, it was still like accreting at 10 to the 5 Eddington or 4 Eddington, and so it wasn't making X-rays efficiently. But then, now we've finally dropped to the, and that's one of the intriguing things about this X-ray excess that Chandra detected is it's roughly at the Eddington luminosity for a 2.65 solar mass black hole. So it's quite an interesting coincidence.
Very good. Very good.
So
I think you got two. You want to talk about any of the other? What we got there? You want to talk about any of the other figures? Big 3, big 4.
I don't know if you want to say anything, Rodrigo.
Figure 3 is mostly a consistency check in which we looked at the energy distribution of mass, and basically we try to estimate whether the fallback rate you get by doing this exercise, so the MDE times the EDT, matches the actual bound rate of change of mass that we measure, and they line up reasonably well.
So this is basically like treating that bound cloud debris as it's kind of like a tidal disruption event. You create a whole stream of marginally bound matter, and you're trying to measure how much mass is at E = 0, because that's the matter that falls back very late.
Yeah.
If you're positive E, you never come back. If you're negative E too far, you come back right away. So you're trying to measure in your simulation how much mass is sitting around the marginally bound line, and does that conform with the rate at which you see matter being coming out in this wind as it falls back. So
okay, good. Well, it's always good to be consistent in what one's doing. Looks like you got some DMDTs and yep.
Yeah, this is just connecting the fallback rate and trying to do it, using the energy distribution, as Rodrigo said, as a consistency check. It seems to work okay.
Yeah, I think you caveated it well enough in figure 1. Yep, it's a consistency argument. Very cool. Very cool. We'll go one last shot there at figure 1 if you like. Very nice. All right.
So may I say one more thing, which is slightly unrelated, more on the simulation side. If you go to the methods section,
yeah, absolutely,
you will see that we use the equation of state of TIMS 2000.
That's got to be wrong. This whole thing is bogus because of that.
So most of the simulations that I have done, at least in the merger context, use your equation of state. So thank you so much for making it public, because it's been very useful.
No, pleasure.
For us over the years. Yeah.
Pleasure.
Just wanted to say that.
Well, thank you very much. I appreciate it. And I'll thank you guys very much for walking through your very lovely APJ letter article. And let me ask, where do we go with this topic, let's say over the next, as a community or your research projects over the next 5 years? Are there additional Spitzer observations being planned? Are there other observational campaigns going on? Can one hope to do several thousand dynamical timescales to push the simulations out further? Or can you change the models to now get into the regime where we're in the years mode as opposed to starting way back at the black hole? Just kind of, where do we go over the next 5 years?
I could say something about the observational front. So yeah, this was a very difficult observation for Chandra. I had to integrate a very long time to get a few photons. And there's a lot of debate as to exactly how Chandra's sensitivity is changing now and degrading. And so this is going to get challenging to get more data. I think there will be, and since things take, now that it's 3 years out, it takes 3 years to see significant evolution. So yeah. I think the observational front will be a little slow. We'll have to come back in 3 years. I didn't say this, but this model for the fallback predicts, there may be a brief phase where the X-rays go up if it's still becoming unshrouded, but eventually it should start to decay right as the fallback rate. Whereas some of the alternative scenarios, which involve the X-rays being powered by an external shock, would predict the X-rays would be flat or rising. So I think if we come back in 5 years, either Chandra or maybe 10 years, if it's Athena or something else, and we do another observation, we should be able to see what's happening. And another thing one could look for is this model predicts that the X-rays are coming very close to the black hole, so they might exhibit time variability, whereas a model where they're coming from some shock on parsec scales will be constant. So I think if we can get more statistics of the X-rays observationally, that's where things are going to go.
Very cool. Yeah, I sort of took the size of the blue square on the right there as a measure of the observational uncertainties, but probably that's not.
That's a whole. If you had the observers, they'd be fighting about that. It's a contentious topic, believe me. I just made the error. We made the error bars big so we wouldn't upset anybody.
There you go. That is very smooth of you. Very smooth. Okay, Rodrigo, where do we go? Let's say over 5 years on simulations. Do we attempt to do 3 million time steps starting from the beginning, or do we change the model and have our initial conditions later or something like that?
So for this specific question of the late time X-ray emission, I mean, Brian said maybe in 5 years we'll get some data. I think there's sufficient time. That's sufficient time to improve the quality of the physics, like GRMHD with better neutrinos and so on, and get to, I don't know, maybe 10 seconds. We've done 10 seconds with bare bones MHD simulations, but we could get 10, 15, maybe 20 seconds with a 3D MHD simulation and get those slopes like to a more reliable place. I mean, we're just extrapolating, right? So if you can get that beginning of the asymptotic phase better, cool. Then we can better answer the question that Brian was pointing to. Does it get under the kilonova and then up again? That's one way. So more generally in mergers, we need to, of course, improve the disk physics, neutrino transport, GRMHD, and also do realistic initial conditions, which get to the question of, was there a jet that punched through some dynamical ejecta? And that is completely dependent on the initial configuration of this thing, right? So more data from LIGO and electromagnetic counterparts would allow us to have more realizations, right? Particular realizations, but more data points, and rather than one data point that can have all kinds of particulars of the shape of the cloud and so on. Right?
So I'll go there, I'll cross my fingers if we get another one, another QLN over there. So,
I'll take another one at 40 megaparsecs.
540.
Well, I just mean that's what this event is so close. That's why we're able to detect this at all, is because it's so close.
It was close. It was relatively right. Okay, very cool. Very nice. Brian, Rodrigo, thank you once again very, very much. And that'll do, everyone. And I hope this made your astronomy day just a little bit better, and we'll see you on the next one. Bye-bye.
Bye-bye.